and specializing the code to the workload that it actually sees running. So let me try and explain this with a simplified example. So this is a sorted function that checks whether an array is sorted. It goes through an array list element by element and compares always two elements. So on the surface, this looks fairly simple, but this is only the tip of the iceberg. So remember, JavaScript is a dynamic language, and I want to show you what's below the water level, basically. So here, first, you can see a function that does array access. You can see a second function that does the comparison. Already, the array access can throw errors. The comparison operation can do type dispatch, and so on and so forth. So there's a whole lot of code that is going on in just a small snippet. When I run this program or this function on just float arrays, then I'm going to speak in the first person of the VM. So when I run this program, I'm going to see that only a very small part is actually exercised. So only those red parts will actually get executed. So it might be nice if I can just take those red parts, put them in a sequence, put that sequence in the loop, and optimize the hell out of it. So this is, of course, not correct, because nobody tells me that all those assumptions will hold in the future. So what are actually the assumptions that I made here? For example, I assumed that I get a float array. I assumed that I won't access the array out of bounds, and so on and so forth. So there's a whole lot of assumptions. And the way VMs in the wild do deal with this problem is they say we have those conditional deoptimization points. So if any of those assumptions do not hold any longer, I need to deoptimize. What does that mean? Well, basically, I need to take the function that's being executed and replace it with a version that doesn't have this assumption. So now, let's look at this from a distance. We have speculative optimizations. So speculation is going on. I optimize under certain assumptions. Then I have deoptimization points in the middle of my function that go somewhere else. And finally, I might want to do compiler optimizations on top of all of that. So is this even correct? Like what could be a correctness criterion? How can I write correct compiler optimizations that interact with the deoptimization point that stay correct when there is speculation in the same function going on? So this is like the initial question. So how did we approach this problem? The first thing that we did is we designed an intermediate language. And this intermediate language does not come from like an actual compiler, but it's more of a model how the intermediate language of a compiler might look like. So the language has many standard features. There is local variables, there is arrays, branches, conditional, unconditional branches, I/O operations, read, print, functions, and so on and forth. So nothing interesting on this slide. But then we added the two features that we needed to describe speculative optimizations. So the first thing is functions have multiple versions. All right. So here I have an example. This is from the previous sorted example. This is supposedly a helper function that lets us access an array. And it's a bit of a contrived example, but let me go with it. So first of all, I want to do a type check on the array that I get. If the array is nil, then I will return nil. If the array is not nil, I'll access the array. And then I'll access it at some offset because supposedly there is like some internal data at the beginning of the array that the VM uses. Okay. Then I have a second version of this function. In this version, I assume that the array is not nil. So I can directly access it. And I have a third version of that function. And here I assume that the user wanted to get index 0. So those are versions. Now, of course, version 2 and version 3 here are not actually correct. It's not correct to invoke them with any argument. So the second ingredient we need is deoptimization points. And now the way we model deoptimization points in Surreer is this one assume instruction. And I'm going to simplify it for a bit and I will come back to the last part in the second half of the talk. So the first thing that an assume instruction has is a list of guards. The guards are Boolean conditions, and if they all evaluate to true, then the assume instruction is basically a no-op. In case any of the guards fails, we will perform the second part, which I sometimes call deoptimization metadata, or just the frame synthesis information. So this part has, here we have two parts. So the first thing is we need to know where to jump to, right? Where to bail out. So this is this f.v.l. And as you remember, we have multiple versions per function. So if we want to target one instruction, then we need to know the function name, the version name, and the instruction label. Then the second part tells us how to synthesize a stack frame that is actually correct for this version. And so the way to read this is that always the expression, the e's, are evaluated in the old context and then bound to the name x, which will give us the new context. So let's look at this in our example. So here, as I said, I want to assume that x is not nil. So I'll put this as the guard. And then second of all, if something goes wrong with this assumption, then I will bail out to the v1, which is my source version, and I'll jump to this L0 right before the branch. The variable mapping part here is fairly trivial because we actually have the same lexical scope in both versions. Let me show you the second or the third version where I have an additional assumption that I is not 0. But also I have this, also another interesting thing is going on here. Because here I actually have a smaller scope. So here, this offset variable I have optimized away. And what I can do is if I need to deoptimize, then I need to reconstruct that variable. And as you can see now, really the right-hand side is an expression, well, a simple one, but it will restore the variable offset with 2. So now this is the basic structure of the IR. At this point, you might ask yourself, okay, now I have different versions, but how do I actually add a correct assume instruction? I haven't explained that at all. So now I want to tell you how you can write a JIT that then later on you can use our technique to verify that it's correct. So the first step is actually we simplify the problem. So what we do is we start with a copy of the source version. We make a one-to-one copy of the source version. In that copy, I can add assumes as much as I want, and it's actually fairly trivial to do because, well, I just go back to the same label, and the variable map is the identity map because it's a copy. And then once I have established this structure, I can now start optimizing the red version here, and I just need to make sure that the mapping stays intact, that the deoptimization points stay valid. So that's the general structure. Let me show it in an example. So again, I bring up the same function. Here, that's the source version. First step, I create a copy. Identical copy, I add one deoptimization point. Make no assumptions, go back to the same point. And now the promise is that I can perform optimizations on just version 2. I don't need to look at the base version anymore. So I'll collapse it. Now, let's start with some simple optimization. Constant propagation, we've already seen it. So here, I have a constant local variable. The interesting part that I want to point out is that I'm not just replacing it in this return instruction, but I'm also just replacing it in the variable mapping. And by doing that, I make sure that the deoptimization metadata correctly maps the relation between this version 2 and the base version 1. Now, the next thing I want to do is like give a precise account what we mean by speculation. So speculation is the following thing. I have any expression, some expression in my program that I want to speculate on. Like, let's say here I have the branch, and maybe, again, I, as the VM that executes this code, have observed that this branch is always taken. So I want to make this assumption. What can I do? I go back to the last assume instruction. I insert this assumption as a guard, and now I can use it for constantly evaluating that expression under that assumption. I can figure out, okay, under this assumption, the branch condition is false. I can remove the branch. Now, those were fairly simple examples. Let's now do something interesting. So inlining. So this is a main function that calls our get function that we've seen before. And what I now want to do is not just inline the unoptimized get function, but I actually want to be able to inline the speculatively optimized get function. So let's see what happens. So here I just took the code of our previous get function. I inlined it into this main function. You can see the array is now called vec, and I is actually 1, because that's the argument to that call. And the interesting part is I have inherited a deoptimization point. Now, does this work? So here's what goes wrong. So in the inlined version, I have one stack frame for main and for get, because I have merged them into one function. The deoptimization point that I inherited from get actually only knows about the stack frame part of get. Moreover, if we deoptimize, we'll deoptimize to a version of get that assumes that it was called by some caller. So we're missing a stack frame of main here. So what we need to do in that case is we need to reconstruct that stack frame to be able to return to. So this is the third part of the assume instruction that I haven't shown you before. And it basically says when I deoptimize, I can synthesize an arbitrary list of stack frames. Let me show you in the example how this looks like. So here I need to synthesize a stack frame that returns to label 0, which is right after the call in main. So this is a technical detail. The results of our calls are named, so I also need to tell the stack frame what to bind the result to. And finally, I need to restore the environment of the main part of the function. So let me switch to something else. When we tried to evaluate the design of Surreer, we showed it to implementers. And so one thing we did is we presented it to the people implementing V8, the JavaScript engine in Chromium. And one thing that they mentioned was that, so I explained to you before that we first add assumes at certain locations, and we don't want to add too many assumes, because as you see, the assume captures all the variables in scope. So it's actually harmful for optimizations. So we don't want to add too many. But now let's assume, now let's say we want to add a guard in a place where we don't have an assume instruction. And they can actually do that in V8. And so the question was, is this more expressive than what we're doing? So it turns out it's not more expressive. What we can do in our case is we can take this assume instruction and we can actually move it. So we take the assume, we move it into the branch, and now I can add a guard only in this one branch, and all is fine. So one interesting point here is that the target of the deoptimization stays fixed. So what does this mean? It means when I deoptimize, I actually go back to an earlier point in execution. Everything I did in between will be thrown away. So there are some rules for assume to when I can move assume, and you can find more about that in the paper. But basically, this captures the intuition that if a guard fails, you can throw away everything you did since the last deoptimization point and go back there. So now let me talk a bit about the correctness part of this work. So this is from if I take a step back, this is how the whole thing looks. So this is how a program looks like. So the blue part is the source code that we got. Then the red part is the speculatively optimized part, and then we have some exceptional control flow going from one to the other. And we want to say something like the speculatively optimized part is equivalent to the source part. But of course, this doesn't work, since there is, like, this argument would be circular. There is a control flow going back and forth. So what we do instead is we need to do something like this. We need to say the source version of our program is equivalent to the source version, the compiler-generated optimized versions, the deoptimization mechanism all together. So this is the general structure of the proof. So we showed this using a weak by simulation. In our in the semantics of Surya, we have 3 non-silent transitions, which is the I/O, print and read, and the stop transition. So we showed that we preserve those. Now, there is one catch. There's one catch. So I've showed you that I can add guards later on. So basically, first we establish correct deoptimization points, and then later in the optimization pipelines, we'll add assumptions, we'll inject assumptions. So of course, our proof needs to make sure that it's always correct to tighten the assumptions. So this is one additional restriction that we need to show. So the restriction is, if you have a deoptimization point, it must always be correct to take the deoptimization, even if the guard holds. Now, when we have all of this, then there's actually an interesting simplification going on. Because I showed you before, it's a 2-step process. So the first thing is we copy the versions, introduce the deoptimization points, and only then we start optimizing. So as you can see on the left-hand side, this is actually the tricky part of the proof, even though it looks trivial, because here we have more states on the right-hand side than we have on the left-hand side. So this was like the technically tricky part. But then if we want to prove new optimizations to be correct, it gets much easier because we only have 2 versions at a time, because the classical compiler optimizations that we showed correct, they will modify a version in place. So here it's actually much easier to show those correct. So again, I won't say much more about this. You can find out more about the details in the paper. So some takeaways. I think if you want to use speculative optimizations, you have to think of deoptimization as being part of the IR semantics. It can't be some mechanism on the side that is separate from your description of what the program is doing. The second thing was, what really helped was to basically have all the information available to the analysis, to the optimizer, and everything. So if you put all the metadata that you need for the optimization in the IR, then it gets much easier to tackle this problem. And then the last observation was that actually proving classical compiler optimizations correct in that framework was then surprisingly easy. So basically the conclusion is, it works. You can use this kind of structure for performing compiler optimizations. All right. At this point, I would like to very much thank the co-authors, and we still have some time for questions.
Really good talk. It is not clear to me whether you're actually implementing sour IR or why you couldn't just use V8s, for instance, or Mozilla's, or WebAssembly or something else.
Right. So the idea was to have more like a model. So we didn't want to take a particular IR because there will be like implementation details in there, but we really wanted to get at the core, at the heart, what is speculation and what is deoptimization. And the idea is that you can take this work, understand how it's supposed to work, and then hopefully apply the techniques to your own IR.
So I suppose that's why you don't have any sort of benchmark, because you can't really do performance for real measurement.
Right. So we're not interested in actually speeding up the program or anything. We were interested in showing what kind of transformations can you do in general, preserving correctness.
Okay, and just the last question. you showed very nicely how you do these transformations. And there's this holy grail in JavaScript, which is actually when you do them. Did you look into that as well?
No,
because you don't want to specialize too much. There's this balancing, this trade-off.
Yeah. No, so this is out of the scope. So we're really concerned with correctness in this scope, in this work, and how you would actually find good assumptions. That's like another very interesting topic. But
thank you.
So I'm wondering, does this first copying the code and, well, it seemed like essentially adding the optimization points more or less randomly, and then later figuring out the optimizations. Is that what V8 really does? I mean, I would think they try to be more kind of guided in where they add the optimization points, so they don't have to move them around later.
Right. So so it depends. So basically, the question is, where can you move your optimization points to? And that's what the question boils down to. And there are some mechanics. I didn't mention them in the talk because of time constraints, but basically, so for example, you probably don't want to move the optimization point over a side effecting instructions, because then when you deoptimize, you will do the side effect twice. So a good strategy is basically to place the assume instructions after every instructions that you can't move over, because then you cover every place. Right.
So I realize this has been about speculative execution speculative optimizations by the JIT compiler, is that right? And then not talking about what hardware does. But,
no, not at all.
Do you have any plans to sort of explore what the effect of these optimizations are on information flow security policies and properties? And if so, what ideas do you have on that?
So currently no plans, but it sounds very interesting. So maybe we can take this offline.
Okay, sounds good.